sp2 hybridization, here we come, whether you like it or not. So in this type of hybridization, we're talking about the central atom, of course. We're not talking about atoms that are terminally bonded. So we're normally talking about an atom and two other atoms at least that are bonding alongside in some shape. And in this case, in this type of hybridization, we have an S mixing with two P's. All right? And then they make three equal orbitals, and they orient themselves in a particular shape based on Vsepr theory. All that means is that these electrons in these hybridized orbitals will repel each other to find the equidistant area where they're the most stable. And that's going to give us the trigonal or trigonal planar shape. It's a triangle in the same plane. So there's only one dimension here, so to speak. As it points out, I can pick this up and make it so it's a planar molecule. Okay, now in this family, unlike the others, we have two members. We have trigonal planar member, and we've got a bent member. And we're going to introduce two new terms. Okay, where the electrons reside is called electron domain geometry, and where the atoms reside gives you the molecular geometry. We didn't have those two terms for sp hybridization because you don't have any of the members besides when they're all filled. That makes some sense. And if you have sp2 hybridization, as you can guess, these bond angles here will be at 120, which is a third of a circle. So let's move down and explain a little bit why it works. Let's take BH3, and if you look at BH3, boron particularly has this configuration, and hope it isn't that boring to you, but the point is, as you can see, 1s2, 2s2, 2p1, how does it get probably an area for three orbitals to be filled with this electron, jumps to an empty orbital with some energy, becomes an excited state, and there we have it. And there we're going to have an S and two P's come together to give me the sp2. Remember, three orbitals in, and you get three equal orbitals out. Okay, so this is going to look like boron, all right, and BH3 is going to look a little like this, B, and it has those three electrons that will repel themselves into that shape. And then, of course, we're going to have hydrogen, who's going to, of course, have one valence electron being 1s1. And that's our shape. And you may see, well, Mr. Grodsky, if I was working backwards and I didn't know this was an sp2 chart, sp2 worksheet, how would I know that this is sp2 hybridization? Well, we start with the dots, and the boron gives me three sets of pairs. Because boron has three valence electrons, we put three out. Now, some people would say, Mr. Grodsky, what about the octet rule? Well, this is an example of an element that doesn't follow the octet rule. Essentially, it has what? 1, 2, 3 orbitals open, or three orbitals with unpaired electrons, and all it needs is what? Electrons to bond with to fill these orbitals. And who's going to give them? The hydrogen. So in truth, it's filling what you can fill. In this case, we're going to fill that. Now, there's no electrons here, so there's no unhybridized P with any electron to think about. So when you do your Lewis dot diagram, and even if you were to write it like this, okay, you say, hey, boron has 3, hydrogen has 1. Even if you were to write it this way, it would not be wrong to put all your H's next to your boron, but you may confuse yourself with the shape. We know that these electrons here are going to repel themselves, and they repel themselves to get what they call maximum stability. And this thing I call Vsepr theory is just the idea that the valence shell bonds, or the electrons in these valence shells, will repel themselves to the most stable shape. So how do we know it's sp2? Do your Lewis dots. I would say spread them out. And then the key here is to count 1, 2, 3, count. There are 3 different regions where electrons can occur around the central atom. And those 3 regions are due to 3 hybrid orbitals. Due to what? One from the S that mixed. I'll just put an S here. and then 2 from p's. Okay, so 3 go in and 3 go out. So that's what you do, is you count the regions, do the dots, make sure that everyone is satisfied in terms of electrons. I know it's not 8 for boron, and he's a little different, but it still works overall if you do this. And from the dots, count how many regions of space. And in this case, we got 3 regions, and that again has to be to 3 hybrid orbitals. So in sp2, there's 1 s and 2 p's for a total of 3. Okay, I'm not going to sketch the non-hybrid molecule. We should know now that the shape doesn't work out if I don't do hybridization or don't use the theory. Again, it's a theory that helps explain. We know this molecule definitely has, I don't know why I just wrote that, a 120-degree bond angle. Okay, so therefore this explains. We also know that the bond energies here to break these bonds are all equivalent. So if you didn't have hybridization, okay, you'd be having what? 2 orbitals with p's bonding, which would be of a lower bond energy because p's are less stable, they don't track them as much. And then we'd have a bond energy that's what? Higher, because it's in a more stable s orbital that has some penetration earlier to the nucleus, as we've learned. So, but the problem is we've learned that all of these bond energies are exactly the same, the energy it takes to break these. And interesting enough, they're somewhere in between these two. So hybridization helps us. We start with the dots, and then we count pairs of electrons, and then we think about how these pairs or these electrons in these hybrid orbitals would repel themselves. In sp2, we're going to get the classic shape of a triangle in the same plane. Okay? And if you had a lone pair, as we'll eventually see, we'll get the bent, a new member of this family. Okay, so I'm going to sketch the orbital diagram. I've kind of really done it here, but hey, I'll just do it again because I'm tall. Okay, we have, here's one sp2, and here's another sp2, and here's another sp2. Yeah. And of course, boron has 3 valence electrons and 3 orbitals of equal energy that blend between an s and a p. Yes. And of course, we're going to have good old hydrogen, which is not hybridized. It's terminal. It has 1 valence electron, so there's an s orbital. Here's another. And that gives us the approximate shape. Okay, orbital sketch. Okay. And that's how we explain it. By the way, these bonds here where we have direct overlap are called my sigma bonds. All right. Now we do, with an sp2 hybridization, do have one unhybridized p that can come into the play. It doesn't here. It would come out of the middle and go back in. So let's start the back side. And I'm starting with carbon here because, in case you understand, carbon we saw could be sp hybridized if you've got some bonds like CO2, but it also can be sp2 hybridized based on the dots. So if it's sp2 with some energy, some of these electrons will jump out here, and if it's sp2, we're going to hybridize the s and 2 p's and leave 1 unhybridized. And you say, well, why do I do that? How do I know? The first step and the best step, do the dots. Do the dots. Do the dots. Let's do it. So I've got carbon. I've got hydrogen. I'm just going to kind of rough draft this. I'm going to pretend I don't know what this looks like. Okay? So I've got 4 H's. So I'm just going to put the 4 H's. And I know that H is terminal. I know it's SN1. 1s1, sorry. So it's always going to fill 1 orbital. So I know very simply that this is terminal, so I know that carbon has to be in the middle. It has more shots at bonding to multiple things because it has multiple open orbitals to share electrons with. So I'm going to put out the valence electrons with the carbon. 1, 2, 3, 4. We should know that it has 4 valence electrons. And this one, I'll make 1 bond here. Okay, as I always say, let's put out the electrons for hydrogen. Not sure if I always say that, but I was going to say something else. All right, now what I'm going to say is let's evaluate. We know the hydrogen has 2, but let's count for the carbon. The carbon unlike the boron I just did, must have 8. It's in a second row element. It wants to fill its p orbitals. So right now it has 4 valence. It needs 4 more to fill that. So it needs to have 8. It needs to share 4 more. So 1, 2, 3, 4, 5, 6. Each carbon is sharing a total of 6. That's not going to work out. Okay? It needs to get 8. So let's get rid of this and go back to where we're working. So let's move this electron and this electron of each carbon and put that to each other to make a double bond. Really all we can do there. And then when we do that and when we evaluate, we get that this carbon, by sharing 2, 1 each from the hydrogen and 2 more from the other double bonded carbon, it feels like it has 8, and this one feels like it has 8. So good stuff here. So we know that we've achieved good stability. So all we're doing is putting out the dots valence electron wise, and then we're confirming that this will probably work. Now I'm going to clean this up, because what do I know? Well, I do know that I have how many regions of electrons? All right, let's go see if we can figure this out. This is going to be one region for this carbon. There's another region for that carbon, and there's another region. Hey, we have 3 regions. That means an S and 2 P's were involved. Hey, this hybridization, imagine that, considering it's an sp2 worksheet, is going to be sp2. Now, I don't like how this is drawn. These electrons are not going to be 90 degrees. That's too much strain. They're too close. They repel themselves. So let's draw it how you normally would see it. Again, if you left it this way, it's totally fine, but you may be confused on your shape. So we have the 2 double bonds in the middle. Each pair of electrons is a bond. And then we're going to have this trigonal planar shape, right? I'm going to put 2 pairs here and 2 pairs here. And notice what I'm doing. Hope you can see the shape is coming out. Now, of course, again, this is totally fine. I like to rewrite it. Here's my hydrogen. Here's my hydrogen. Here's my hydrogen. And here's my hydrogen. If you can't see it, all right, open your eyes. Okay, this is the trigonal planar shape. Each what? Carbon has that trigonal. So we have 2 trigonal planars in the middle. Remember, it's always about the central atom. And if we were to pick this up and turn it this way, this would be a plane. Okay, it'd be on the same plane. So this is screaming sp2 hybridization. Okay, so I'm going to get rid of those little sticks right there so we can look at it better. All right, now, what do we know about the bonds? Well, I'll tell you this. The bonds between carbon and carbon are going to be nonpolar. Well, because they have the same attractive or electronegativity. We use the word electronegativity to talk about how well the nucleus can pull other people's electrons because of its effective nuclear charges or its Z number, all the things we've learned. So we kind of put that all into one word there, electronegativity. Now these have the same, so they're nonpolar, so these are right down the middle. What we should know is that carbon and hydrogen have about the same electronegativity. Now in truth, okay, carbon is about 2.6 for carbon. Hydrogen is about 2.2. So there's a 0.4 difference. And you may say, well, that should make a polar bond. Well, no, it doesn't. We consider this bond to be so small in difference in electronegativity, we consider a hydrocarbon bond to be nonpolar. So all of these bonds we're going to consider to be nonpolar. Now, in a Regents chemistry exam, they consider 2 different elements to be polar, but in the whole world of chemistry, we consider to be nonpolar. Now, what about the molecule? Well, if I look at the molecule, again, I always think of polar molecules, draw a big circle around the molecule. Is there a region more rich in electrons than others? And the answer is no. Because of the symmetry, there's no place where there's more electrons than other. This is evenly distributed with its electrons. There might be more in the middle, but you can't get to the middle. What side of this molecule has more electrons? Well, there isn't. So therefore, this is a nonpolar molecule. Now, a really good thing to do is to think about, is there an overall dipole moment? Now, because we're going to consider that these are nonpolar, there's not even a single dipole moment. But if there was, these arrows would cancel out. So this is a nonpolar molecule. All right. All right, bond angles. We know it's 120 because the hybridization that we got by counting the what? We counted the what? areas of electrons around the central atom, including lone pairs. Okay, so that's 120. Now you notice we got two words here, electron domain geometry and molecular geometry. How is that going to happen? Well, electron domain geometry is the geometry of the central carbons, including where the electrons are. So I've got one here, and one here. Electron domain geometry is trigonal, right? Planar. I'm just going to kind of abbreviate here because I don't have room. Now, what's the molecular geometry? Well, it's exactly the same here because wherever I have three regions of electrons, I also have atoms in those positions, right? Don't forget, each carbon here represents a sp2 orbital that had to come out. So there's what? It's also trigonal planar. When would it be different? Well, if this was a lone pair, we'd only consider where the atoms are, okay? So we'll keep going through that. So let's go through an orbital sketch to really understand what it means to have that double bond there, okay? So let's keep doing that. And I don't know why I'm writing that twice, but here I'm doing it. Okay, so again, this is trigonal planar. So let me draw some sp2 orbitals around the central carbon. So this carbon is going to have an sp2 here. All right, sp2 here. Ooh, that guy's a little bigger. And then an sp2 here. Good times. So sp2 always will have three orbitals around the central atom. And then we're going to have another one directly overlaps to make that sigma bond. sp2, sp2, sp2. Okay. Shapes. Okay, now we're going to draw my hydrogens, which are just the S's. Let's put out some electrons here. Now let's put the valence electrons out for the hydrogen. For the hydrogens, yes. So we have, let's do a different color. Let's do blue. So each hydrogen brings one valence electron. Cool beans if beans are chilled. Now, let's put out the valence electrons for the carbon. 1, 2, 3. Whoa, it needs some place to go. There's a fourth place. This is for this one. 1, 2, 3. But it also has one more. And if you haven't forgotten, the one more has to go in an orbital that wasn't hybridized. So sp2 is going to have one electron for each of these carbons that is unhybridized. So let's just draw that. Okay, give it a special color because I can. Now it's hard to do this to really make some sense of this because these are really planar. So this is really coming at you and going into the board, but I'm going to draw it straight up and down. We can try to use our imagination. And so I have another unhybridized P using our imagination. And guess what, party people? Let's put our valence electron. This has the what? So this is 1, 2, 3, 4 for this one. 1, 2, 3, and 4 for this one. And you can guess, okay, that our what? This is going to be our pi bond. So we've got our sigma bond here and our pi bond above and below. A little more simpler in structure than the ones we've been drawing for sp. But if you notice something, the first bond is going to be our overlapping bond, our sigma bond. Our second bond is that perpendicular bonding called the pi bond, a weaker bond. Okay, so think of these as being planar. And if you think you're looking at them from the side, this is going up and going down. And this is the sketch of the orbital diagram, somewhat anyway. And it explains the fact that the pi bond is a little bit weaker. And this is very symmetrical. Electrons are evenly distributed throughout the molecule. Okay, and we explain the second bond is pi. Don't forget, if you've got a double bond, you need unhybridized P's. And guess what one sp2 hybridization gives us? It gives us one unhybridized P. So if you remember, sp hybridization in the other worksheet gave us two unhybridized P's for the chance of a triple bond. Now being sp2, now we only have one, so therefore you're going to see a proliferation of double bonds only in this area. Okay, so that could be another hint as we go through this. All right, so C2H3Cl. Very similar. Let's draw the dots. We always start with the dots. So we've got C2. Now I'm kind of going to be guessing. I have 4 things. I can put 2 H's. I already kind of know what's happening here. It's the same structure, isn't it? Except I'm going to replace an H with a what? A Cl. So we can quickly go through this. And carbon has 1, 2, 3, 4. It's the same structure. The same idea of how I did this is over here. This carbon is 1, 2, 3, 4. This hydrogen brings 1 to the table. This hydrogen brings 1. And this chlorine brings 7 because it has 7 valence electrons. I have to draw all of them. Okay? Now, if I wanted to do this, I can do a Lewis dot diagram with dashes. Okay? And you can be dashing. Yeah, that didn't go over well, I know. So here's my H. Here's my single bond to the Cl. You have to show lone pairs that are non-bonding on the chlorine. And here's my H here. Okay, no lone pairs on my H. How is this different? It's the same exact thing except these two. Do we have polar bonds? You bet your pony. Don't want to say donkey. You bet your pony. The carbon and Cl are very polar. So yes, you have polar bonds. We know that the hydrocarbon bonds, okay, too close in electronegativity to, in fact, have what we call polar bonds. So this is the only polar bond. Is it a polar molecule? Well, because we have an element pretty good at pulling electrons this way, we're going to think about a molecule where there's some richness of electrons on one side, and that side is where the chlorine is. This other side doesn't have that richness of electrons or electron density, so it's positive. So this is polar. There's an unequal distribution of charge due to that chlorine there. Or if you want to use a more simpler understanding, it is asymmetrical. Okay? Now, of course, if something is polar, you need to show an overall dipole moment. What's a dipole? Well, between the carbon and chlorine is more electronegative, so it gets a little partial negative. It pulls this pair of electrons closer. I really should be drawing that closer. So between here and here, this is the negative part of the bond. This will be the positive part of the bond. And we always draw our dipole moments from positive to negative to show that flow of charge, okay, or at least a heaviness of electrons pointing this way. And because there's no other arrow, for this vector quantity that has direction and size for it to cancel, this is the overall dipole moment. And I expect that if something is polar from now on in. A lot of expectations, sure. I have great expectations. Okay? Certainly not as much as the book. Yeah, it's a bad one. All right, so we have hybridization, sp2, of course. Why? When I do the dots, count the pairs of electrons surrounding the lone pairs. 3, bond angles, 120. Electron domain geometry, it's a trigonal or triangle planar. This is trigonal planar. Okay, why? Because the molecular geometry, where the atoms are, still gives me a triangle. Don't forget, here's my triangle for that carbon. And where's the triangle for this carbon? There they are. All right. So there's atoms in those positions, so the molecular geometry is the same as where the electrons are. Now, in terms of drawing this, I'm going to cheat. I'm going to take off a what? A carbon. And now because chlorine is terminal, because it only bonds essentially right now, because of its 7 valence electrons, I'm going to bond it at the end. So if you can see with me, this would be an unhybridized p orbital. Boy, this would be fun. One going up and going down, one coming at you and into the board. This is not my best one, that's for sure. We have 1, 2, 3, 4, 5, 6, and 7. Okay, and that would be that shape right there. Okay, of course, this one was nonpolar. Now the chlorine makes it polar. All right, moving forward. AlCl. Now, aluminum chloride is a metal nonmetal. Some people think that that is ionic. It's actually more covalent, something in between, but same idea. What do? You got to get the dots. Yeah, get the dots. So aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. So its valence shell is 3s2, 3p1. So you can see it being under, okay, boron, it also has 3 electrons. So I'm going to draw the 3 electrons kind of equally distributed. You don't have to, but I know that they repel themselves in 3 different orbitals. I'm already thinking what? Yeah, hybridization. And the chlorine, well, we know what about chlorine? Chlorine's going to have 7. So this chlorine brings 1. And we have to show the lone pairs. Chlorine brings 1, 2, 3, 4, 5, 6, 7. And I'm done. Again, you say, oh my gosh, how can that work? The octet rule is not being satisfied. Well, boron and aluminum can do this, and certainly they do, and it is an example of what kind of hybridization? Count the regions of electrons around the atom. There's 3. I knew that by putting out 3 electrons. I knew that was going to happen. I'm so tall. Okay, so the hybridization had to occur from what? sp2, 3 orbitals, an s and 2 p's. Bond angles, gosh darn it, if it's in this family, 120. All right, so it's easy to understand. This is 120. And of course, what's the electron domain geometry? Trigonal, planar. Why? Because I have electrons in 3 positions that repel themselves. What's the molecular geometry? Where the atoms are, same position, is also trigonal planar. Now, what kind of bonds do I have? Well, we consider these to be somewhat polar bonds, so we can say polar bonds, yes. And polar molecule, hope you can say no now. It's pretty simple to see that the electrons are evenly distributed. Even though we have 3 polar bonds, they're what? They are equal in their unequalness all the way around. There's no real difference in this molecule. And of course, to draw this, very simple, although I'm not really good at drawing these guys, but I'll draw here's one, here's the second one, and here's the third, and these are all sp2 orbitals. Okay, I put out the valence electrons for the aluminum, or as we say in England, aluminium. That's really weird, but I'm all good with that. And then, of course, I'm going to put the chlorine in. Oh, chlorine's valence electron. We know it has what? We know it has 7. So we know it's terminal at the end, so I don't need what? I don't need hybridization to explain that, so I'm going to have a p orbital here. See if I can reclaim my status as drawing these. Hard on the pad. And then there's my Z1 going in and out. I draw my S's smaller so people can see the P's. I keep saying that because people yell at me if I don't let them know. And of course, this has 1, 2, 3, 4, 5, 6, and 7. And now by sharing, it feels like it has 8. And I would do this 2 more times. Okay? And I'm not going to keep doing it. You can for fun. You can look at my key when I post it. So that would just be another example of another one there for the same way. Show all the valence electrons. Okay? Now, this is a nonpolar molecule because of its symmetry. Now, if you think about the vectors, the dipole moments, let's just put that here. Aluminum and chlorine. Chlorine is more electronegative than aluminum, so chlorine is the negative part of the bond. Aluminum is the positive part. So what you would have is what? Always point toward the negative. We'd have 3 arrows of equal magnitude, equal size, that's what a vector quantity is, going in 3 different directions. And believe it or not, these 3 vector quantities would cancel out. If I tied you up to a post there, pulled you in 3 directions, and you were infinitely strong, you wouldn't go anywhere as long as these arrows were pointing in a 120-degree bond angles, and we're pulling equally as strong. That's what we're saying here. These forces would cancel themselves out, and there is no net dipole. That's why it's nonpolar. All right, so let's go to the hardest one here, and the one that's the most interesting is NO2 minus. This is a polyatomic ion. In our table, table E, regents, or tables I've been giving you, we haven't explained how these clusters of nonmetals can actually have, okay, a charge. So let's start. All right. So you don't know anything about it, so you put an N. Yeah, let's put two O's. Who cares? We don't know. We're going to move these around. So nitrogen has 1, 2. I have a habit of putting my 2 electrons for N on top because it's so known to have those 2 lone pairs. So that's why I always do that. But hey, 1, 2, 3, 4, and 5. I could have put 1 here. Oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now you say, well, maybe I just need 1 electron here, and this would be 8 for oxygen. We have 8 for what? This oxygen by sharing 2, but this one only has 5. So we have some issues here. Nitrogen, being that it's what? 1s2, 2s2, and then 2p3. There's its 5 valence electrons. Its unfilled energy level, n equals 2. Wants to have, 3 more, okay? Wants to share 3 more to have the 8 at octet. It definitely wants an octet, unlike the ones I've been showing you. And more often than not, that octet rule can be used for second row elements. Now, so what I'm going to do is I'm going to take 2 of these electrons and make a double bond here. Again, these are just dots on a page, and we put out all the valence electrons, and now I'm trying to just figure this out. So I move these 2 here. And this is more helpful. Oxygen still is 8, and if you can't see it, draw a circle. All right? And that now has the 8. Oxygen, of course, is 1s2, 2s2, 2p4, so it wants to share 2 more. Happy, it's got its octet. This nitrogen, okay, 2, 4, 6, 7 needs 1 more, and this oxygen has 7, needs 1 more. So for this to work, we need an extra electron. So you can see where the negative comes from. So there's an electron sitting in the environment that this pulls. Okay, and you say, well, why would it do that? We've been down this road before. When we have NO2 -1, and we do the oxidation states, the whole thing has to equal -1. Each oxygen is -2, -4 overall. What charge must nitrogen be individually for this to be -1? Well, you've guessed it, +3. So what we have is a +3 charged kind of ion sitting around these very electronegative oxygens who are basically pulling in electrons. So clearly, this is electron sink. This is an oxidizing agent as well as just being an ion. Okay, so let's clean this up. All right. Now, we have to start thinking about our shape. We did our circles, we figured this out, and I'm going to put in an electron right here that came from the environment. And as soon as I do that, I have to put brackets to show the entire thing is -1. Very important. This became an ion, just like when we do ionic bonding. Now, I'm going to clean this up because I may confuse myself to think that this is linear. The first thing we ask ourselves is, after we have figured out the what? The amount of electrons that each one of these had to have by putting dots around to be stable, we're going to count regions of electrons, bonding and non-bonding. There's a lone pair, okay, around the central atom. And we count 3. And S and 2 P's came together to make sp2 hybridization. Gosh, that sounds familiar. So we clearly have hybridization is sp2. Bond angles must be 120. Aha. Okay. Now, so what happens, party people? Okay. What happens was I want to clean this up to make more sense of this. So I'm going to have an N with a lone pair. Then I'm going to have a bond, which is a pair, and the O. I must show the lone pairs here for the oxygen, and a double bond here for this O. And it has just 2 pairs. This bracket -1. Okay, now, why did I bend it that way? I put it in the shape of the trigonal planar because that's the electron domain geometry. I don't have room for it, but we'll put TGP. Yeah, it's a new restaurant, TGP. Thank God for planar molecules. All right, probably not going to catch on. But the point is, the electron domain geometry is the same because everything that is sp2, the electrons are arranged always in electron domain geometry. But now we've got this lone pair. The molecular geometry is not going to be trigonal planar. We've got to consider where the atoms are. So really what we have is this molecule where you have something here, something here, something here. It's the triangle of this is now gone. So this we call as a bent shape. So the molecular geometry for this guy is bent. It's different than the electron domain geometry. Do not forget, we started this fantastic lecture thinking about what? The two members. We have trigonal planar and we have the ability to be bent. Now, electron domain geometry will always be trigonal planar if we identify sp2 hybridization for the central atom. Bent occurs as another member of this family if you've got one lone pair, and it's only going to be for the molecular geometry. The electron domain geometry will always be, okay, the sp2 trigonal planar. So that's important as we go through these different families. Okay, so back to reality, up there goes gravity. Now, let's try to understand what's going on with this molecule. It's a little advanced, and I'm going to introduce something that's new. Now, you may have noticed that when I draw this, I have a double bond on this side and a single bond. Who's to say that I could not draw exactly the same thing, lone pair up top, make a single bond here, and a double bond here? Who's to say I can't do that? And because I can do that, that's one way to identify something with resonance. The word resonance means that these molecules, or these shapes, these proposed shapes, or these Lewis dot diagram structures, each one is -1, okay, resonate back and forth between these. It doesn't mean it's this one or this one. It actually means there's a blend of both of them. Meaning there's not a double bond here. There's kind of a 1.5 bond on both sides. Point sides. Okay? And how does that occur? How can we have the ability to have a double bond on this side? Some people might write it this way. Here's the N, and here's a single bond and a single bond. Here's the lone pair. And some people write dotted line to show that there's a kind of half double bond here and a half here. How can electrons jump back and forth? Well, this idea of resonance occurs because there's something called what? Delocalized electron. Why are they delocalized? Because somehow they have the ability to move through the N. Now, what gives us that ability? Ha ha ha. Okay, we can find that through the structure. Before we do so, do we have polar bonds? Yeah, we can say so. Is it a polar molecule? Well, determining if this is a polar molecule is like asking the number 5 if it has marital status. Okay? That doesn't make any sense, does it? You can't ask an ion. This entire bracket is -1. This entire stretch is -1. So there's no polarity. So anything that is an ion, okay, it's non-applicable. You can't answer that question. Okay? It does have polar bonds, but the polar molecule is non-applicable. Doesn't make any sense. I can speak. Now, one more point before I answer the final question on why this can occur. This bond angle I put is 120, and I'll accept it. When you have a lone pair, though, when you have a lone pair, that means you don't have another nucleus of another atom pulling this pair of electrons out. So having a lone pair actually means it is actually closer to this nucleus, what actually bends these guys down even more. So this bond angle is actually not 120 anymore. It's like 117. But I'm not asking you to know that number. 120 works for sp hybridization. Just be aware a lone pair will push these in a little closer because these electrons are going to be held closer to nitrogen since they're not being held equidistant toward another nucleus of another atom. Okay, last little piece. How can this be resonance? Okay, well, Let's draw this to find out. I'm going to do my best. Now I'm going to draw this planar. So I'm going to kind of look, here's my eyeball, and I'm going to kind of look at this structure, which is planar. I'm going to kind of look straight on that way to see if I can draw this. All right. So we have our N, which is sp3, and we're going to have one that is going out. I'm looking flat on it. I've got another one that's coming out, and I've got another one coming out. We're kind of looking like as a flat shape. I know it's tough. And we have the two lone pairs of the nitrogen way over there. And then I have the what? Okay, this has 1, 2, okay. And we'll maybe put one here. Who knows? But what do we know with sp2? Aha! It's got a what? An unhybridized p that goes through the top and down through the bottom. Why is that important? Okay, let's get rid of these pair of electron right here for a second. Feel bad now, I'm over it. And let's have that coming out. We're looking at it like flat. Okay, well, it has 1, 2, 3, 4. Now what's on the end? Well, we have the oxygen. Oxygen is what? It's got this one sticking up too, hey. And it's got that one coming at you and into the board. Don't forget my S, unhybridized. And the same thing happening here. I've got my unhybridized P overlapping here. I've got this PY in the same plane. And what's happening? Okay, not an easy one to figure out. I would never make you draw one like this, but I want you to see what's happening. 1, 2, 3, maybe 4. Now let's go with the oxygen. 1, 2, 3, 4, 5, 6. I just did all the valence electrons. And what can you see? Oh, there's a double bond. I can get with that. All right. And this oxygen, 1, 2, 3, 4, 5, 6. Well, it's got one hanging out. Well, wait a minute. Who's to say that this one can't move this way? And then this one moves over this way? We don't know. So the reason why we can move electrons from the P back and forth and have a blending of the two is because the central atom, the N, has an unhybridized P. And it allows the resonance to occur. If we didn't have an unhybridized P, we couldn't have electrons that are not being localized. They're being delocalized. Now they can flow through the entire top and bottom of this molecule, and that gives it stability. Okay? So kind of introduced a new term, resonance now, and we'll get to that. And we introduced the idea that we can have something called a polyatomic ion, which means you have to add an extra electron to make it work. If it was -2, I'd add 2. Hope you really enjoyed that. Thank you and good night.